In this lesson, we're going to be looking at applications of exponential functions. We talked last week about exponential functions, how to solve them, what their graphs look like. So in this lesson, we're going to look at how are these types of functions used in real-world applications. So we're going to be looking at models of population growth. We're going to be looking at radioactive decay, and then we're going to be looking at compound interest and using the number E. Remember, we talked about E last week. So in our first example, a biologist is culturing bacteria in a large petri dish. She begins with 1,000 bacteria, so that's important information, and supplies sufficient food so that the first 5 hours the bacteria population grows exponentially, doubling every hour. So we're going to find the function that models this population growth. We're going to then determine when, after how much time the population reaches 16,000 bacteria, and then finally we're going to calculate the population, how many bacteria were there after 2.5 hours. So first thing we're going to look at is we're going to come up with the exponential function, okay, for this scenario. So we've got P of T. That stands for my population at a certain time. Remember exponentials, then it equaled your growth rate, however much it grew, times your base to a power. So here my growth rate is P sub 0, and that stands for your initial amount. Here, how much bacteria did I start with? Times A to the T power. Okay, so I can plug some things in. I know I don't need P sub T right now. That's going to be in my equation. So I'm going to have P sub T equals P sub 0 was my initial amount. It said that this biologist started with 1,000 bacteria. And then A stands for how much did this thing grow by. Okay, it grew, it said, let me go back and read it. It grew, it doubled every hour. So that is my growth rate here. So it's going to be times 2 to the T power. I don't know what time I'm looking at. We're going to be able to plug into that in a little bit. So this is my exponential function. This is what we're going to be using now to go and solve parts B and C. So part B, we wish to find the time T for which P of T equals 16,000. So at what specific time, after how many hours did I have 16,000 bacteria in my petri dish? Well, if we remember, our equation is P of T equals 1,000, that's my initial, times my growth rate of 2 to the T power. So all I'm going to do here is take this 16,000 and I'm going to plug it in for my P of T. So I'm going to get 16,000 equals 1,000 times 2 to the T power. I'm going to solve for my time. I want to know how many hours it took. So it's going to give me 16 equals 2 to the T. We talked last week about how do we solve these exponentials. I have to get like bases in order to solve them. So I can rewrite 16 as a base of 2. That is 2 to the 4th equals 2 to the T. Remember, when I have like bases, then all I have to do is take those exponents, set them equal, so T equals 4. So that means after 4 hours, there will be 16,000 bacteria in my petri dish. And then the last part of this one, to calculate the population. So now I want to know how many bacteria will I have 2.5 hours after I start this experiment. So I'm still going to use that same function. P of T equals 1,000 times 2 to the T power. This time I know what T is. It's 2.5, so I'm going to plug it into my equation. So I want to know this time, how many bacteria do I have? What's my population? I guess I should change this to, what is my population after 2.5 hours? Equals 1,000 times 2. T is 2.5. And then you're just going to take it, you're going to very easily just plug all that into your calculator. Again, remember, you can use the Desmos link on Google Classroom if you need a scientific calculator. And then once you plug it into your calculator, you get that after 2.5 hours, there is about 5,657 bacteria that should be present in that Petri dish after 2.5 hours. Okay, now we're going to look at radioactive decay, and for some reason this slide did not convert well, but it says determine the base A so that the function, it should be A of T equals A sub 0 of A of T. Accurately describes the decay of carbon-14 as a function of T years. Okay, so we're going to look at this. So this time we are not increasing, we're actually decaying. We are decreasing, so our growth rate will not be bigger than 1. Our A value will be between 0 and 1 because we are, again, decaying. So what we know is that half of the original amount of carbon-14 decays over a period of 5,728 years. So A of 5,728 will be half of my A sub 0, my original amount. Okay, it says that this thing halves. So that means that my A value is 1/2. Okay. So then I'm going to go through and I'm going to solve this. Okay, that means, let's see. So that means that we are left with A to the 5,728 equals 1/2 here. So every 5,728 years, half of my radioactivity or my radioactive whatever I have gets cut in half. Okay, at this point you're going to need a calculator because in order to solve this for A, to get what A actually is, we're going to have to actually anything to raise to power to solve it, we take the root of it. So we actually have to take the 5,728th root of 1/2. Okay, and that actually gives me that A is approximately 0.999879. So that means for my function here, I have that A of T equals A of 0. I don't know what that initial amount is. I don't know how much carbon-14 I started with. Okay, it tells me that every 5,728 years it goes down by 1/2, but I don't know what I started with. And then, sorry, my screen flipped. And then my A value here is at 0.999879 raised to the T power here. That's my equation. And then compound interest, again, for some reason this formula did not convert well. But most of us know about interest when we have say we put in money to a savings account in the bank. The bank holds our money. It actually takes it and uses it and gives it to other people. But while it's holding our money, they pay us interest. Okay? Now, vice versa, if we go and take money from the hospital through a loan, say you're going to go buy a car and you need a a car loan, okay, the bank's going to give you up front how much money you need, but as you pay them back, you're paying them extra money. You're paying them that interest. And a lot of times it is compounded interest when you're talking about investments and things like that. So the actual equation, since it didn't come up correctly, is A of t equals P times 1 plus R over N raised to the NT power. Okay. So what does all this mean, all these letters, okay? A of t here is the amount that I have after a certain amount of time, after 5 years, after 2 years, after 1 month, whatever, how much money I have. P is my principal. Okay, that's how much I kind of start with. And then I'll multiply it. Here's where I get my interest and stuff. 1 plus R stands for the rate. Okay. And N stands for how many times per year that it's compounded. So if it's compounded quarterly, then your N would be 4. Okay. Yearly, your N would be 1. Okay. If it's done monthly, then N would be 12 because there's 12 months in a year. You got N here twice in this formula down in the denominator, and then it is in the exponent. And then T just stands for time, your number of years. Okay, so Sandy invests $10,000 in a savings account, earning 4.5% annual interest compounded quarterly. Okay, so we got some stuff here. 10,000, 4.5%, and we are compounded quarterly. What is the value of her investment after 3.5 years? Okay, so let's see what all we have here. We know that our equation, so again, it is A of t equals P times 1 plus R over N to the N times T power. Okay, so what's my time? What are we looking at here? 3.5 years. So I'm going to do A of 3.5. This is what we're solving for. This is my amount after 3.5 years. P is my principal. Either how much I put into my account or how much money I take away from the bank. She invests $10,000, so that's going to be my principal, times 1 plus, then my rate is 4.5%. Now I can't put that percent in. I have to change it to a decimal. So to do that, I move my decimal 2 places to the right. So it's actually 0.045. That goes 0.045 divided by N. How many times a year does this thing compound? If it compounds quarterly, there are 4 quarters in a year, so that's going to be 4. And then it's going to be raised to the N times T. So 4 times, what is my time on this thing? 3.5. Now, you can take your calculator and you can plug all of this one side into your calculator, or you can do it in little parts. That does not matter. But after 3.5 years, once you plug this into your calculator, Sandy should have something around $11,695.52 in her account. Okay, so that's how much she should have in her account after. Okay, so that means she's gotten some interest. Now, really quick, could I figure out how much interest she got? And I could. All I'd have to do is take the amount that she has in her account now, that $11,695, and subtract how much she put in, the $10,000, and that will give me how much interest. So she made about $1,695 of interest over that 3.5 years. Okay, example 4. 9 months after depositing $520 in a monthly compounded savings account. Okay, so we got $520. and this compounds monthly. Frank checks his balance and finds that the account has this much, $528.84. Okay, that's how much is in his account after a certain amount of time. Being the forgetful type, he can't remember what the annual interest rate was for his account, and he sees the bank is advertising a rate of 2.5% for new accounts. Should he close out his existing account and open a new one? Okay, so first thing we're going to need to do is identify our quantities, and we've pretty much done that here. We know that our starting amount, our principal, was 520. Our N, how much is it compounded? It compounds monthly, so N is 12. And our T, it says after 9 months. So really quick, what is our time? 9 out of 12 months gives me, this can reduce to be 3/4, which is 0.75. So that's going to be my time when I'm looking into this thing. And then we know that after this certain amount of time that he has $528.84 in his account. So I can go through and remember we're going to be using this equation. A of t equals P times 1 plus R over N to the N t power. A sub t, how much do I have over this amount of time? I have $528.84. My original amount was $520 times 1 plus my rate. That's what I don't know. That's what we're trying to find out. N, this compounds monthly, so there's 12 months, all raised to the 12, times, what's my time? 0.75. Okay, and I'm going to solve for R here. That's what we're wanting to do. So to do that, I'm going to get 528.84 equals 520 times 1 plus R over 12. And I'm going to go ahead and multiply that 0.75 times the 12. And that gives me my 9 here. Okay. The next thing I'm going to do is I'm going to solve this for R and divide by the 520 on both sides. And that's going to give me 1.017 equals 1 plus R over 12 to the 9th power. I've got to get rid of that 9th power before I can get the R by itself. And to do that, I take the 9th root. And that is going to give me 1.001875. It's approximately equal to it. 1 plus R over 12. Okay, I'm going to keep going. I'm going to keep solving this thing. I'm going to subtract that 1 over. I'm going to get 0.001875 equals R over 12. To get the R by itself, I'm going to multiply by 12 on both sides. And I should get that R, my rate, equals something like 0.0225. So what is that percentage then? Okay, because this is the decimal part. I want to change it to a percentage. Do that by moving me back 2 spaces. So I've got about a 2.25% interest rate here. Okay, so, but the question's actually asking me, let me go back to it. So we know our annual interest rate. He sees that a bank is advertising a rate of 2.5%. Should he close out his existing account and open a new one? So 2.5 compared to 2.25. then we need to say that the 2.5 is higher. So Frank would gain more money by switching accounts because the interest rate is higher. Okay, and that's what I just wrote out. Thus, Frank's current savings account is paying an annual interest rate of, said, 2.25%. So he would gain a slight advantage by switching up to the 2.5%. Okay, looking at the number E here. The number E is defined by the value of 1 plus 1 over m to the n power. And then this should say as m approaches infinity, as it keeps getting bigger and bigger. Therefore, E is just this number here, this long 2.718 number. In most applications, though, we just approximate it and we use the decimal 2.7183. Okay, that's accurate enough for us in these situations. Okay, continuous compounding formula. An investment of P dollars, again, P is our principal, compounded continuously. Okay, that doesn't mean that it's compounded every month or every quarter. It is always compounding every minute, okay, every day, at an annual interest rate of R. And again, for some reason, these formulas didn't convert over, but the formula is A of T equals P times E to the RT power. Again, P is our principal. E is that number 2.7183. R, when the exponent, is our rate, and T is our time. So if Sandy, last seen in example 3, has the option of investing $10,000 in her continuously compounded account, earning 4.5% annual interest, what will be the value of her account in 3.5 years? So we've got our principal, $10,000. We've got our rate of 4.5%. And we've got our time of 3.5 years. Okay, we want to know how much money will she have in her account. Okay, so we're going to look here. We just said all that, so we're going to plug in. I want to know how much money will she have after 3.5 years. Well, her principal is $10,000. Okay, times E. Since I'm using E because this thing was continuously compounded, to the R power, well, my rate, again, 4.5%. I got to move it 2 places. So it's going to be 0.045 times T, which is 3.5. And then you can take and plug all this into your calculator. Remember, when you plug all this into your calculator, some calculators have the button E and you can use them, or you can put in the 2.7183. Does not matter. You're going to type all of that good stuff into your calculator. Okay, and when you do that, the account earns about, well, when we solve it, our amount here is $11,705.81. Okay, so if I go back and look, though, what did she get? I'm flipping way back. What did she get before? $11,695. So it's pretty much kind of wanting what is the difference, okay, of these two accounts. So how much more does she earn? Okay, so all I'm going to do, if I want to know how much more she earns, I'm going to take this number here, the 11,695, and I'm going to subtract it, let me get back, from the 11,705, which means that she earns somewhere about $10.29 more with it compounding continuously than it compounding quarterly. Okay, make sure that you take notes on this, and there is a lesson on Hawk's Learning this week. I will also later this week be posting another video on log applications in the real world. So make sure you get the exponential application assignment on Hawk's Learning finished.